Hey guys, welcome to topic 3.02 phase changes. You might wonder what happened to topic 3.01. I don't have a tutorial video on it. Well, in my class, my students are going to be responsible for teaching themselves this using reading material. But I'll quickly do a quick review of the phases of matter. First of all, we have several phases of matter that we can deal with, but we're only going to be looking at the three basic ones: solids, liquids, and gases. The properties are very straightforward. Solids have atoms arranged in a regular crystal lattice, and the molecules are not free to flow past each other. They merely vibrate in place. They have a definite mass, like all matter does, a definite volume that remains constant over time, and a definite shape. Liquids, well, let's say you take a solid and you heat it up enough so that the molecules loosen from each other and are allowed to flow freely. Liquids have definite volume, but they will take the shape of whatever container they find themselves in. For example, a puddle will simply take the shape of whatever depression in the ground it happens to find itself in. Liquids have definite volume, they have not definite shape, and they have very strong attractive forces, though not as strong as solids. In order to turn a liquid into a gas, you have to completely eliminate any forces of attraction between the molecules. Gas molecules are extremely far apart. When you turn a liquid into a gas, the volume will increase by at least a factor of 1,000, where the molecules will get very far away from each other and therefore not attracted to each other. They move around without any resistance whatsoever. They have no definite shape, they have no definite volume, but take the shape and volume of whatever container you put them in. So my molecules can flow past each other, but have no resistance to flow. But have resistance to flow due to intermolecular attractive forces. That would be a liquid. By the way, resistance to flow is called viscosity. My molecules are held in a rigid geometric pattern and cannot be moved relative to each other. That would be a solid. My molecules arrange themselves to take the shape of whatever container they are put into, but they occupy a definite volume. That would be a liquid. And my molecules are not at all attracted to each other and are free to move around without resistance. That is a gas. And so, based on the properties of these phases, you can easily identify what phase it belongs to. A sample of this phase has very strong attractive forces that make the sample have both a definite shape and volume. Of course, that would be a solid. Today, what we're going to look at is the changes that these phases can undergo to transform from one into another. And they all have to do with attractive forces. Solid molecules are very strongly attracted to each other. Liquid molecules are less strongly attracted to each other, and gas molecules are not attracted at all to each other. So changing the phase relies on you being able to modify the strength of attractive forces between the molecules. To turn a solid into a liquid requires you to add heat. We call this process melting. The heat that you add will weaken the attractive forces enough to allow the molecules to break out of their crystal lattice and be able to start flowing freely past each other. If you remove heat from a liquid, you are now going to remove the energy that allows the molecules to move past each other, and this will strengthen the attractive forces and cause the liquid to freeze. This takes place at a specific temperature, called either the melting or the freezing point. It doesn't matter what you call it, it's the same temperature. For water, this temperature is 0 degrees Celsius, or 273 Kelvin. And during the process of changing phase, the temperature remains constant. So it doesn't matter how much heat you add, as long as there is both solid and liquid in the container, the temperature will remain constant. So if you take ice and heat it up, the temperature will rise until you hit the melting point. And once it begins melting, so long as there is both liquid and solid in your container, the temperature will remain at 0 degrees Celsius until the phase change has completed. Liquid to gas. In this case, you're taking strong attractive forces and utterly destroying them by adding heat. When you add heat to a liquid, you're weakening the attractive forces to the point where the molecules simply break free of each other completely and are allowed to roam wherever they want. When you remove heat from a gas, you're removing the energy that allows them to flow freely, strengthening the attractive forces and turning the gas back into a liquid again. This takes place at the boiling point, or the condensing point if you like, and for water, this temperature would be 100 degrees Celsius or 373 Kelvin. And just as in with melting or freezing, during the phase change, temperature remains constant. You see this pot of water sitting on the stove. Well, it's boiling. It's at a temperature of 100 degrees Celsius, and so long as there is both liquid and gas in that container, the temperature will not change. It is impossible to get liquid water above 100 degrees Celsius without modifying it in some way. So we'll talk about those modifications a little bit later. One of those modifications you'll learn about in this unit, another modification you'll learn about much further down the road. There is also the possibility of completely skipping the liquid phase. If your substance has weak enough attractive forces, heating the solid will allow it to turn directly to gas without the formation of a liquid phase. When you add heat to a solid, and it does this, it's called sublimation. When you remove heat from a gas and it turns into a solid, it's called deposition. And it takes place at the sublimation point. Now, there are not a lot of substances that do this because on Earth we have, we don't really have all that many natural liquids on Earth, but most of them will go through the phase changes of melting and boiling. But there are certain substances that will turn directly from solid to gas. What you're seeing in this container is carbon dioxide. Solid carbon dioxide has such weak attractive forces that it cannot form a liquid phase and turns directly into a gas. Interestingly enough, on Mars, water does the exact same thing. Now, why should this be the case? You'll learn about that later when we take a look at vapor pressure. So if the attractive forces are too weak to sustain a liquid phase, a substance can transform directly between solid and gas. This is a phase change diagram. What it shows you is the changes in temperature that occur as you add heat to a solid. And as the phases go through their changes, the differences in temperature. So if we start off with, let's say, water, we're going to assume this is water, and we start at a temperature of minus 40 degrees Celsius, and we add heat to this, what will happen is the temperature will increase as we add heat. Now, you'll notice this lovely crystal lattice right here. That will not change throughout this whole process. The only thing that will happen is as you add heat, the molecules within the crystal lattice will vibrate faster and faster. Once you hit 0 degrees Celsius, the vibrations are so fast that molecules of water begin to break free of the crystal lattice. And you get your first drop of liquid right here. And as you continue to add heat, there's more and more liquid and less solid. But you'll notice that as this process continues, the temperature remains at 0 degrees Celsius. Solid cannot exist above 0. Liquid cannot exist below 0. So while you have liquid and solid together, the temperature will remain at 0 degrees Celsius until that phase change has completed. At this point right here, the last tiny bit of solid has melted away, and 100% of your substance is in the liquid phase. Now, as we add heat to this newly liquid water, the temperature will increase. The molecules will flow faster, and the viscosity will decrease. And once you hit that boiling point of 100 degrees Celsius, the liquid will begin to boil and molecules will start to break free into the gas phase. At this point here, you start to see the first bit of gas forming. Now, that is not entirely true. This is an oversimplification because, as you may be aware, liquids can evaporate. But for the purposes of this explanation, let's assume no evaporation. When you hit the boiling point, you can tell because bubbles of vapor begin to form inside the liquid, rise up through the liquid, and break free. And the vapor is released. Here we have the vapor, the gas phase, and here we have the liquid phase. We have both of them. Here we see the first bubbles of vapor forming within our liquid. And then it begins to bubble more and more vigorously. And as we proceed, as we continue to add heat, the amount of liquid we have decreases and the amount of gas we have increases. The temperature remains a constant 100 degrees during this whole time. You can't have liquid above 100 degrees. You can't have gas below 100 degrees. Well, that's an oversimplification we'll address in another topic. But once the last drop of liquid has completely boiled away, now you are left with nothing but gas. And as you continue to add heat, the temperature of that gas will increase. Now you're going to notice I have some formulas here. You remember in the last unit we did Q equals mc delta T. Well, delta T is temperature change. And as long as the temperature changes, we can calculate how many joules it takes to make the temperature change. When the temperature changes, we can calculate how many joules it takes to make that temperature change. But notice that during a phase change, temperature does not change. So if we want to calculate how many joules it takes to melt a solid or boil a liquid, we can't use mc delta T, because there is no delta T. We have to use a different measure, which you'll learn about in the next topic, called heat of fusion and heat of vaporization. That will be in the next topic. Okay, so how do we interpret a graph like this? Here's some actual data with some time and temperatures here. So let's say we start off with a solid at 200 degrees. We heat it up, and at minute 4, at about 273 degrees Celsius, it begins to melt. So A and B is the solid phase. Now, between B and C, the melting occurs. It turns from a solid into a liquid. And we have both phases while this takes place. Between C and D, we have entirely liquid. Between D and E, we have liquid and gas as the boiling takes place at a temperature of 373. This is for water here. And then from E to F, you have the gas phase. So let's suppose I said, for how many minutes is this substance in a phase where the molecules are free to flow past each other but maintain definite volume? Well, that would describe a liquid. So we're looking at line segment CD. This segment starts at minute 8 and ends at minute 20, and therefore 12 minutes will occur during this particular time. What if I asked, how many minutes occur between the first drop of liquid forming and when the substance is entirely a gas for the first time? Well, the first drop of liquid forms as the melting begins, so B represents the first drop of liquid, and that occurs at minute 4. It's in a gas entirely for the first time at point E, which is at minute 34. So from minute 4 to minute 34, 30 minutes will have elapsed describing that. For how many minutes is this substance entirely in a phase that has both definite shape and volume? Well, this would describe a solid, and it is a solid from minute 0 to minute 4. Therefore, it will take 4 minutes for it to be a solid. For how many minutes is this substance in a phase that has no definite mass or volume? Well, all substances have definite mass. Even gases have mass. That's why we have atmospheric pressure. So there is no situation where a phase will not have mass. Therefore, that question is a trick question and cannot be answered other than to say it would spend 0 minutes in this mythical phase that could not exist. For how many minutes does this substance exist as both liquid and gas simultaneously? Well, it's liquid and gas between D and E. D is at minute 20, E is at minute 34. Therefore, 14 minutes will elapse. How many minutes will it take for this substance to melt? Well, it begins the melting process at B and ends the melting process at C. Therefore, from minute 4 to 8, 4 minutes will elapse. And so that's how you can interpret a heating curve. Next topic, we're going to take a look at how much heat it takes to make these phase changes happen. But until then, I must bid you adieu, and I hope you had an absolutely wonderful morning, or afternoon, or evening, or wherever you're watching this. And once more, bye.